All right. So last time we stated this theorem, which tells us the following. Suppose we have a measure space, probability space, omega, A, and P, and N denotes the class of all negligible sets. What's a negligible set? It's a subset. It may not be measurable. However, it is contained in a measurable set whose measure is 0. That's why we call it measurable. Okay, sorry. That's why we call it negligible. And this proposition tells us the following. By just joining those negligible sets to our algebra this way, okay, by just taking unions of elements of the algebra with the elements of the negligible class, we obtain another algebra which contains both A and N, and this algebra contains all of its negligible sets, okay, and we will call this completion of the algebra N, okay, sorry, A. And moreover, the probability measure, which is defined on the original algebra A, is extended to the completion this way. Measure of a subset A union a negligible set, which is a typical element of the completion, is just defined to be the measure of A. Okay, so this way we extend our algebra and the probability measure on that algebra to the completion of A. Okay. For finite, measure spaces or probability spaces, this doesn't mean anything because there we take usually all the subsets as measurable sets, and our measure usually is the counting measure. So there you don't have, negligible sets and so on. However, if your sample space omega is infinite, like real numbers, then it has so many subsets. And usually our algebra is a small portion of that, like, Borel sets, which are unions and intersections of open sets and their completions and so on. And there we have lots of other sets which cannot be measured. However, among those, there are some whose measures, although we cannot measure them, they are contained in some measurable sets whose measures are 0. And this way we just include them into our algebra, and our algebra becomes complete. This will have some, theoretical advantages we will see later. Okay, now let's see how we can prove this. Okay, now clearly, this A bar, which is the union of A and N, this gadget. So it's the union of this collection of the unions of A and N's. Okay, this is contained in the sigma algebra generated by A and N. Okay. Next, we will show that. Okay. We will show that A bar is a sigma algebra which will imply that A bar contains the sigma algebra generated by A and N. Okay, which would finish the proof of the first part. Okay, so let's do that. So we claim that A bar, which is A union N's, A is in A and N is a negligible class, is a sigma algebra. Okay. For this to be sigma algebra, we have to prove that countable unions of elements of this collection is an element of the same collection. So let okay an uh, n be a countable class in A bar. Well, then of course we know what the union of this. Then of course this gadget, and from 1 to infinity is what? This is the union of A ends and the union of N ends. Okay, where this gadget, the first one, is in A since is in A since A is a sigma algebra. What about this gadget? If this is an element of N, then of course this union will have this form. So we would be finished. So we have to just prove that this is a negligible set. Okay. So to finish the proof, we just need to show that this gadget is a negligible set. How can we show this? Well, since each and N is negligible, there is a measurable set, there is a set, there's an element Bn of the algebra so that Nn is contained in Bn and the measure of Bn is 0, right? This is the definition of being negligible. Well, then, of course, we have what? The union of Ns is contained in the union of Bn's, and this union is an element of the algebra because each Bn is an element of the sigma algebra. Moreover, what is the measure of this? Moreover, measure of this gadget, P of the union of Bn's, what is this? Well, we know that this is less than, right, the sum of the measures of each one, right? And this is of course something non-negative, but we know that all of these has measure 0, so this is 0, and therefore this gadget has measure 0. Hence, thus this is a measurable, so this is a negligible set. Is a negligible set. So we are done. Okay. What we have shown is that I took a countable collection, and the union of the elements in this collection is written as an element, as the union of an element from A and an element from N. Okay. Okay. So this gadget, maybe I can write it one more time like this, is an element of a closure. Okay. Also, I have to prove also that the complements of such things are also in the algebra, right? So uh, to finish, to show that this A bar is an algebra, uh, we need to prove that this thing is closed under completion. Not completion, complement. Taking complement. Okay. So so let A be an element of the algebra and an element of the negligible set. Choose B in A with N is contained in B and measure of B is 0. I can do this because N is negligible, right? Well, then let's see what is the complement of this gadget, right? This is a typical element of A bar, and I take its complement. Well, this is just okay. A union N complement intersection with B union B complement. Why is that? Because B union B complement is the whole space, right? This is the whole space, omega. So I am taking the intersection with omega. I will get, of course, this gadget. All right. Now I will write this as follows. This is A union N C intersection B union A union N complement intersection B C. Okay. All right. Well, this is just let me write it here. This is just uh, A union N complement B in union A complement intersection N complement intersection B complement. Yes. Why is that? Because the complement of the union, this thing is just A complement intersection N complement. So you take intersection V B complement also. So this is what you get. Okay. All right. Now this is equal to this gadget union. What about this? Well, since N is contained in B, N complement contains B complement. Therefore, the intersection of these two is just B complement. So this is A complement intersection B complement. So this thing is equal to this one, okay? Because N is contained in B. So when you take complement, N complement is N complement contains B complement. Therefore, the intersection of the two is the smaller one. All right. So we have obtained this. Now, note that uh, note that J, okay. So this is B. Sorry, there's no set called C. Okay, thank you. Şimdi şunu biliyoruz. A complement intersection B complement is in A since A and B are in A, right? These are elements of the algebra, therefore their complements are in the algebra, and therefore their intersection is in the algebra. What about the other one? Also, note this. A union and C intersection B is contained in B, right? And measure of B is 0 by its choice, and thus, this gadget, whatever it is, it may not be measurable. However, it is contained in a set, measurable set whose measure is 0. Therefore, this is negligible. Okay. Is a negligible set. So what we have obtained is then our complement of A union N is written as an element of the algebra A and a negligible set. So this means hence A union N C is in a bar. So in particular, so this finishes the proof that this concludes the proof that A bar is a sigma algebra. Okay. Okay, now what is next? So this finishes the proof of the claim, and therefore, yeah, we finished the proof of the first part. Now for the second part, what was it? So let me just remind you, what are we going to prove? We have to prove that this formula defines probability measures on this new algebra. First of all, we have to show that this is well defined. What we mean, I may choose different n's here. For different n's, the measure of A union n is defined to be A. So for this to be well defined, we have to show that for different n's, this doesn't make a difference. So let's first see that this gadget is well defined. First, we must show that P bar is well defined. Okay. For this, let A1, A2 be elements of the algebra and N1 and 2 elements of the negligible class so that A1 union N1 is equal to A2 union A2. So these are the same elements of the algebra A bar. Well, since they are the same element, their measures has to be the same. But the measure of this one is defined to be the measure of A1, and the measure of this one is defined to be the measure of A2. So for P bar to be well defined, the measure of A1 should be equal to the measure of A2. So for this thing to hold, we must show P of A1 is equal to P of A2, because this thing is defined to be P of A1 and this thing is defined to be P of A2. So let's see why this is the case. Okay, now note the following. Since A1, efendim? Okay, yeah, all right, thank you. A1 union N1 is equal to A2 union N2. This, since we have this, we have the following. A1 difference of A1 from N2, and then difference of N2 from A1 is contained in N1 union N2, right? If you have some element here, but if it is not in A2, then it should be in N1, N2, right? So if you have something here in A1, but it is not in A2, so it has to be in N2. And similarly, if you have something here and it is not in A1, then it has to be in N1. Therefore, the difference, these two union of these two differences is contained in this set. However, you know, these are two negligible sets. Therefore, their measure is also 0. Since I have also this A1, sorry, A2 intersection, this is empty, right? The difference difference of A1 from A2 and difference of A2 from A1 are disjoint sets. Therefore, we have the following. We have we obtain, oops, what? Measure of A1, A2 plus A2, A1. This is, since they are disjoint, this is equal to A1, A2 union A2, A1. But this measure, this thing is 0 because this gadget is contained in N1 and 2, and N1 union N2 is negligible, right? its measure of each one is 0, and they are contained in some set. This is contained in some B1, this is contained in some B2, so that B1 and B2 has both measure 0. Therefore, the union has measure 0. Therefore, this gadget, this is something measurable, although this is not. This may not be measurable, but this thing is, measurable, and it has measure 0. All right. So, in particular, of course, in particular, uh, well, so the sum is a, is 0, and moreover, each summand is non-negative because they are probability measure, some probabilities, they are non-negative. So both of these must be 0 because they are non-negative. Yes. And finally, A1 can be written like this. A1 intersection A2 union A1 difference A2, right? And since I's are all measurable sets, these are elements of the algebra, so that I can take their measures, and hence P of A1 is equal to P of A1 intersection A2 plus P of A1 in difference A2, but this thing has measure 0, this thing has measure 0, so therefore this is A1 intersection A2. But similarly, one can repeat the same, argument for this one. Similarly, P of A2, right, is equal to P of A1 intersection A2 because argument is symmetric, and hence P of A1 is equal to P of A2. So P bar is well defined, hence P bar is well defined. Okay, our claim is more than that. We claim that P bar is also a probability measure. So it has to satisfy two conditions. First of all, it should be never, uh, uh, negative. That's clear because it is defined to be P of something. But it has to also satisfy the condition that whenever you have a disjoint union of a countable collection, then the measure of that is the sum of the measures. So next we need to prove the followings. What are they? P of something, A union N, is always positive. Well, this is by definition just P of A, and this is 0. So this is clear for all A. So elements of A bar, right? A typical element of this algebra has this form. Therefore, I can use this. Okay, we proved this. And the second, let an union n from 1 to infinity is a disjoint uh, uh, class, we have to prove that the so we must prove uh, what measure of this gadget is equal to measure sum of the uh, measures, right? And this is not difficult either, but I will not do that. So I will leave this as an exercise. Uh, this is leave as an exercise. Okay. I will finish this section by the following definition. The probability space omega a bar p bar is called or will be called the completion of the probability space sigma sorry omega ap. All right, any questions so far? So this way we can always assume that any set, any negligible set is an element of our algebra, right? If it is not, you just combine those into the algebra, you obtain a bigger algebra, and your measure extends trivially to this bigger algebra, and now those negligible sets are elements of your algebra. Okay, so there's no harm assuming that negligible sets are elements of your algebra. Okay, well, in the next section we will consider so-called probability and classical schemes. Here we will usually consider finite measure space, and we will consider problems of probability which are you are familiar from maybe even high school years, counting arguments and so on. So this the next section will be about that. The title of the section is this: interpretation of probability and classical schemes. Okay. All right. So let omega be a finite sample space. A uh, a Boolean algebra. Since your sample space is finite, there is no need to consider right infinite unions. Therefore, a Boolean algebra is fine for our purposes. Boolean algebra of all subsets. Okay, so we take the uh, uh, you know, biggest Boolean algebra, and P be a probability measure on A. It will be usually the counting measure, but it doesn't have to be. Okay. Uh, suppose that assume that omega has n elements, and each element of omega has the same probability 1 over n. So it is not the counting measure, but weighted counting measure, because you know uh, the whole space has measure 1, and each element has the same measure, and it has n elements. Therefore, the measure of each singleton must be 1 over n, so that the sum is 1. If A is an element of A, so it's a subset of omega, is an event, then its probability is what? Uh, so it is just this is a finite set, so it is just 1 over n times the number of elements in A, right? Each element in the sample space, each singleton has measure 1 over n. Therefore, if you have a set of, let's say, k elements, then the measure of this will be just k over n. So this is just what? This is just actually the number of elements in A divided by n, which is the number of elements of the sample space. Okay. So in probability theory, this is called the scheme of equally likely outcomes. Hence, to find the probability uh, of a given event, it is important to count the number of elements of uh, it contains. So number of elements in the event, okay? Okay, so here is a definition. This is the definition of discrete probabilities. So let me just give you the definition. Let A be omega i's and this is a countable subset of omega, and pi, okay, I in z, no, not z, sorry, I, a set of probabilities no, set of positive numbers such that the sum is equal to 1. So this is not necessarily a finite sum. It is a countable sum. It might be a countable sum. Then this collection determines uh, a measure on the power set pek de doğru değil. Burada omega yok, tamam, doğru. Power set yeah, okay. Defined by this formula, P of B, just sum of pi's if omega I belongs to B. So A is a countable set. Therefore, any subset of A is a countable set. You look at the elements of this subset. Each element has a probability. You just sum those probabilities. This sum is always convergent because the sum of all the omega i's is 1. Therefore, if you take a proper subset of that, it will be something probably less than 1. But it's a well-defined function. This clearly extends to any sigma algebra A of subsets of omega containing PA by defining şöyle tarif edebiliriz. C'nin measure of C is just PI. So you just count the elements in C which belongs to A, okay? You don't count the ones which are not in A. Such a probability is called uh, discrete. In the second hour, I will make one example. Okay, so let me stop here now. I will give an example in the next hour. All right, now let's give a break.